Hi, welcome to this video. Now, in this video, we are preparing ourselves for paper number 2, Physical Chemistry grade 11. So now here we're going to start with question number 7. But now before we can most definitely answer the questions, let us firstly read the statements and the questions. So now question number 7, it reads as follows. They say to us, ammonia reacts with water to produce ammonium ions and hydroxide ions according to the following reaction. Now, this type of reaction can also be regarded as acid-base reaction because you know that ammonia, it is a base, and water, it is an acid. In this case, water, which will act as an acid because you know that water can be an ampholyte, will have to donate its proton to ammonia, and then ammonia will accept that proton as a base to form these products that we see over here, these ions that we see over here. So now, 7.1, it says to us, define a covalent bond. Now, how do we define a covalent bond? We have 3 types of bonds that we have learned. We have the covalent bond, ionic bond, and the metallic bond. Now, covalent bond is a type of a bond that exists between the 2 non-metals. So between 2 non-metals, we are talking about the covalent bond. And the bond between those 2 non-metals, they will be sharing the electrons, okay? So now, how do we define it? We say it is the sharing of the electrons. Okay, let me write my answer over here, 7.1. 7.1, we're going to say it is the sharing of electrons, okay, between what? Between between two non-metals atoms, okay, or molecules. So this is how we define a covalent bond, okay? Now we move to 7.2. Now 7.2, it reads as follows. It says to us, the ammonia molecule gains a hydrogen ion from the water molecule to form the ammonium ion, as much as we discussed from this chemical reaction. So 7.2.1, it says to us, name the type of bond between the ammonia molecule and the hydrogen ion, okay? So now the type of bond that exists between the ammonia ion and the hydrogen ion, that will be donated by water. It is called the dative covalent bond, or you can call it the coordinate covalent bond, okay? So now we know that the ammonia, if we have to write the Lewis structure for ammonium ion, we know that N, which is our nitrogen, will be surrounded by 4 hydrogen atoms. But you have to understand that here we're going to have the shared electrons between these 2 over here. Let me show you something. So now these were lone pairs of ammonia, but because water has donated hydrogen ion into ammonia, and therefore we're going to have a molecular structure that looks like this, whereby this hydrogen will share, even though this hydrogen didn't contribute any of the electrons, but this hydrogen over here will share the lone pairs of ammonia. So this type of a bond between this hydrogen and this nitrogen, this type of bond, it is called the dative covalent bond, or it is called the coordinate covalent bond. So 7.2.1, to answer the name of the bond between the ammonia molecule and the hydrogen ion, it is called the dative covalent bond. Remember, you can call it dative covalent bond, or you can also call it the coordinate, okay? Or coordinate covalent bond. Okay, it is different. It is most definitely different from just covalent bond. Okay, I hope that was clear. And then we move to the second question, which is most definitely 7.2.2. Now 7.2.2, it says, using Lewis notation, write an equation to show the formation of ammonium ion. So this is what is happening. How did we form the ammonium ion? The hydronium ion from water will be donated to ammonia, which is what we were told over here, 7.2. Basically, we are going to write the chemical equation based on this statement of 7.2. So now, how are we going to do that? This is how we're going to do this. So I'll just answer my question, which is 7.2.2 over here. Okay. I'll just answer it over here. So 7.2.2, we see that the ammonia, but you remember we're going to use the Lewis notation, not the chemical notation. We're going to use the Lewis notation. So let us draw a Lewis structure for ammonia, okay? So now we know that ammonia, it has nitrogen at the center. This is the central atom. And therefore, what is the valence electron for ammonia? For nitrogen. So meaning it's going to be surrounded by 1, 2, 3, 4, 5. 5 number of electrons, they're going to surround nitrogen. How do we see that? How do we know that nitrogen is going to be surrounded by 5 electrons? You refer to your periodic table. Nitrogen, it is in group 5. So that means the valence electrons for nitrogen, it is 5. So that means here we're going to have 1, 2, 3, 4, and 5. So this is the valence electron for nitrogen. But at this point in time, nitrogen, it is not happy. Why? Because it's supposed to obey an octet rule. It's supposed to be surrounded by 8 electrons. So now remember, we have 3 hydrogen atoms that are left, which will bond with our nitrogen. So how many hydrogen do we have? Remember, it's 3. So that means 1 hydrogen will come at this point by donating its electron, and 1 hydrogen will come at this point by donating its electron, and another 1 hydrogen atom will come at this point and also by donating its electron. Now let us check the number of electrons that surrounds our nitrogen. 2, 4, 6, 8. Now nitrogen has obeyed what you call an octet rule. It is stable and happy wherever it is. So hydrogen, it is an exception of an octet rule. It does not matter. Hydrogen is supposed to be surrounded by 2 electrons for us to say it is stable, meaning the outer energy level of hydrogen, it is now fully occupied. And we know that hydrogen can be fully occupied by only a maximum number of 2 electrons. Now, this is the Lewis structure for ammonia. But because we want to write the chemical reaction, what does the ammonia actually react with? The ammonia will most definitely react with hydronium, hydrogen ion. But remember, where does the hydrogen ion come from? It comes from water molecule, okay? And therefore, now this is easy because remember, hydrogen ion, we call it a proton. It doesn't have electron at all. We know that hydrogen from the periodic table, it is found in group 1, period 1, and the atomic number for hydrogen, it is 1. So that means hydrogen has 1 electron, has 1 proton. So when you talk about the hydrogen ion, we are talking about the hydrogen that do not have electron at all. Hence why we call it a proton. Sometimes we call it a proton or we call it a hydrogen ion. So this proton will most definitely be donated to our base, which is ammonia. Okay, and therefore now this reaction will go as follows. Remember, we are drawing our chemical reaction using Lewis notation, hence why we use the Lewis structures. So now, when interaction happens between these 2 species over here, what will be our product? So remember, we're gonna form an ammonium ion, whereby this hydrogen will most definitely come here to these shared electrons to form what type of a covalent bond? A dative covalent bond. Because you can see that this hydrogen will share the electrons, will share the lone pairs of this molecule. Hydrogen didn't contribute any electron. So that means in this case, we're going to have a dative covalent bond. So here we have the lone pairs, whereby this hydrogen atom will come along, and therefore these, they have been there all the entire time. These have been there all the entire time. This one came with its electron for ammonia, electron for, sorry, for nitrogen, electron for nitrogen. This one came with its electron, this one came with its electron. And therefore this is the molecule. And therefore now, because this molecule, it is positively charged, it's an ion, therefore we write the brackets and then we write the positive charge over there to show that this, it is an ion that is positively charged. And therefore for 7.2.2 you get your full marks, which is 4 marks for using Lewis notation, writing an equation to show the formation of ammonium ion. That's how we solve this. So now question number 8, it reads as follows. It says to us, here we are talking about the physical properties, okay, of our substances. There are many different types of physical properties. We can talk about the boiling point, the melting point, the vapor pressure, the viscosity, the tension. There are many different types of physical properties, but what I've realized is here in grade 11 you just focus only on specific physical properties such as the boiling point, the vapor pressure, as well as the melting point. So now 8.1, they want us to define the boiling point. Now, what is the boiling point? I think the word itself, it's easier to understand it because, I mean, like, we live in a world where we use many things around us. Like, for example, when you boil water, water has what we call the boiling point. Each and every substance that you can think of, you can think of alcohol, you can think of water, you can think of any type of a liquid. Any type of a liquid has its specific boiling point. But now, what is this boiling point? The boiling point is what? It is the temperature at which a vapor pressure of a substance will be equals to the atmospheric pressure. Now I'll explain that so that it can make sense, okay? So now to answer, let's just answer it first and then I'll do explanation based on that. So now question number 8.1, it says to us, define the boiling point. I'm saying to you, the boiling point, even the melting point, each and every time, okay? Let me give you a tip. When we define these physical properties, you start by saying the temperature at which, even the melting point, the temperature at which. That's how we start by defining them, okay? So the boiling point will be the temperature at which, the temperature at which the vapor pressure of a substance is equal to the, okay, you can say external pressure, you can say external pressure, or you can say just atmospheric pressure, okay, is equal to the atmospheric pressure. This is how we define the boiling point. But you want to understand, what does this definition actually mean? I'm going to give you this definition using a drawing so that you can understand how do we see it. Let me define this using a drawing so that it can make sense to you. So say, for an example, we have a pot, right? A pot, a cooking pot. We have a pot, and this pot, it is placed on a stove. Okay, it is placed on a stove, and we light up our stove. Now, this is what is happening. Let's say the pot here, it has a liquid, right? It has a liquid, which is water. We have water in this pot, right? Now, this is what is happening. When you boil water, what do you expect? What do you expect to happen with this water? You expect this water to boil, right? But now, when you have a pot like this is what is going to happen. We have what you call the vapor pressure. The vapor pressure, it is the vapor, meaning it is the steam, okay? The vapor pressure, it is the vapor that will rise out of the surface of the water molecule. Now, this is the water, right? Immediately when you see the steam rising from the surface of this water. This steam, it is referred to vapor, meaning this is the vapor, right? But now this is what is happening. We have air around us, all right, around our pot. We have air. Air, it has what we call atmosphere, right? So now this is what is happening. The vapor pressure of water, when it is equals to the atmospheric pressure, meaning the pressure by the air molecules, because we have air around us, right? We have air around the pot. So when this pressure, when this air molecule and these steam molecules, they experience equal pressure, it's the temperature that we're gonna read from the stove. It is called the boiling point of water. I mean, I can put two different liquids. I can put water in the pot. I can put any type of alcohol in a pot. When I boil these two liquids, they're not going to boil at the same temperature. Why? It's because they have different boiling points due to the intermolecular forces that are found within each and every substance. So in this case, because now I have water, the atmospheric pressure and the vapor pressure, they will be equal. When the vapor pressure and the atmospheric pressure are equal, therefore we are talking about the boiling point of this substance. Hence why I'm saying to you, when you define the term boiling point, you say the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. That's how we actually define the boiling point. So now 8.2, as a chemical student, you need to have a basic understanding how these things actually work. Because as you continue with chemistry or chemical engineering, you're going to face these things a lot. So now 8.2, it reads as follows. It says to us, the boiling point of the first four hydrides. Now, first four hydrides. So what are the hydrides? Our atoms or our molecules are bonded to hydrogens. So these atoms, they from which group of our periodic table? Group number 7. We call them the halogens: fluorine, chlorine, bromine, and iodine. We can see that all of these atoms, they're from group 7 from our periodic table, and they are called halogens. They are bonded, all of them, they're bonded to hydrogens. And so they are called the first four hydrides. Why they say it's first? Because from the periodic table, the first element is going to be fluorine, chlorine, the following one will be bromine, and the following one will be iodine. Okay, so molecules with hydrogen of group 7 elements, we know that, are similar in the table below. Now we have first four hydrides. These first four hydrides, they have different boiling points. As much as I told you, I can have water and alcohol. The boiling point of water, each and every substance, guys, each and every substance has its own specific boiling point. Something can boil. Water, we know it boils at 100 degrees Celsius. When the temperature is about 100 degrees Celsius, you'll start to see the steam rising from the surface of water. The moment, I don't care, the moment you see the steam, you won't be able to see with your own naked eyes. But the moment the steam starts to rise, that's an indication that shows the atmospheric pressure is equals to the vapor pressure. Therefore, the steam will rise at this temperature. If you give water this temperature, the steam will start to appear, or the vapor will start to appear from the surface of water molecule. So now, here the hydrides are 4, and they have different boiling points, meaning HF will boil at this temperature. HCl will boil at this temperature. You see, HBr will boil at this temperature, will start to boil at this temperature. Okay, fine. Now, 8.2.1, it reads as follows. They say to us, describe the trend in the boiling points from HCl to HI. They eliminated HF because HF loses the trend. So that means we're going to focus from HCl to HI. Okay? Now, when they say describe the trend, this is what they want from you. Each and every time, guys, when you see this term, describe this trend, give the trend, whatever the trend, this is what they want you to do. They want you to talk about whether is a certain thing increasing or decreasing or remaining the same. When they say describe the trend, they want you to tell us the relationship. Okay, they want you to tell us the relationship between our variables. So now let us talk about the trend in boiling point from HCl to HI. So now what is happening with boiling point? Is boiling point increasing? Is boiling point decreasing? Is boiling point remaining the same? That's what we need to do. This is a simple question because you can see from the graph. So to answer from the table, so to answer 8.2.1, how to describe the trend? Look, what's happening with the boiling point of this moving from this direction? -84, -66, -35. We are increasing. We are not decreasing. Be careful. We are increasing, meaning from this huge negative number to this small negative number. That's an increase. Mathematically, we know that, right? We are increasing. So the trend is the boiling point. The boiling point. The boiling points from I can say just increases. The boiling point increases from where? We're stating it, right? The boiling point increases from HCl to HI. Then that will be your final answer. We are done. Answering that question is only 1 mark. And you don't need to complicate life over there. You just answer according to what you see. I hope that was clear. Now, 8.2.2. It says to us, explain the trend. Now we are explaining, we are not describing, right? Explain the trend identified in question number 8.2.1. So you're going to explain why is boiling point increasing. We said the boiling point is increasing, right? Which is true. But now we're going to explain that. Why? Why is it increasing? Now, the factors that affect the boiling points. Let's have a look at these molecules. These molecules, they're from the same group. But what is different about this? It's the molecular mass. When you go to your periodic table, we have hydrogen, hydrogen, hydrogen. Okay, the molecular mass for hydrogen is the same throughout. But the problem is here we have Cl, here we have Br, and then here we have I. So the molecular mass of HCl and HBr and HI are not the same. Now, the molecular mass of Cl, when you go to your periodic table, it's 35,5. But the molecular mass for Br, it is 80. And then the molecular mass for I, it is 127. So that means the molecular mass increases. So as the molecular mass increases, we say that the molecular mass, it is directly proportional to the boiling point. The higher the molecular mass, the higher the boiling point we're gonna have. It's easy as that. So we can see that from HCl to HI, the molecular mass, or you can say the molar mass of hydrides or molecules of hydrides increases, right? From HCl to HI, the molecular mass of hydrides increases. Increase in molecular mass requires more energy to break. Therefore, therefore, the boiling point will thus increase. Therefore, the boiling point will thus increase. Let me tell you this. It does not matter how you answer these questions. I know some of the learners, they're like, we're supposed to answer it in this way and in this way. I'm going to tell you why, okay? What matters is, do you have the keywords that make sense to this? We're all different and we cannot think the same and we cannot cram. That's not how you learn. Okay. I assess learners to understand, not to cram. Now, this is what is happening. When you answer this question, the keywords that are needed, it's this, okay? From HCl to HI, the molecular mass of anhydrides increases. Increase in molecular mass requires more energy to break. Okay, I forget this, due to increase in intermolecular force. So this is what is happening. We can see that when the molar mass increases, the strength of intermolecular force becomes strong. Therefore, for you to break that strength, you need more energy, right? You need more energy. Therefore, if more energy it is required, therefore we're gonna have high boiling point, because energy that is needed is gonna come in a form of temperature, which is heat, right? Energy can come in many different forms, which is heat. So that means for you to break, so that this thing can boil, you need more energy, right? So that means more energy is required. So that's why I'm saying to you, increase in molar mass will increase, or you can say increase in molar mass will increase intermolecular force. Therefore, more energy is required. When more energy is required, therefore, the boiling point will thus increase. You can put it however you want, but this is what I want you to know. Talk about increase from where to where or decrease from where to where. That's the first thing. The second thing, you talk about the intermolecular force, which leads to energy. That's number two. Number three, you talk about the boiling point. You talk about number three, you talk about the BP, which is called the boiling point. You talk about the boiling point that will result due to the strength of intermolecular force and increase in energy. These are the most important things that you need to talk about when you are referring to the trend, when you're explaining the trend of the boiling point of your molecules. I hope that was clear. It does not matter how you explain it, but these are the keys that you need. Now, 8.2.3, it says to us, and then you get your 3 marks, okay? One, two, three, by talking about these 3 things that I have just mentioned. 8.2.3, it says to us, by referring to the strength of intermolecular force. Remember, here we spoke about the intermolecular force, but we were not specific. There are different types of intermolecular forces. London force, which is called dispersion force, or mutual induced dipole force, and then we have the dipole force. We have the hydrogen bond. We all know those different types of intermolecular forces. So 8.2.3, it says, by referring to the strength of intermolecular forces, explain why the boiling point of HF is higher than the boiling point of HCl. Now we are comparing 2 species. So we are talking about the HF and HCl. Now the HF is the only one that has the positive boiling point, and that's a very high boiling point. That's a very high boiling point of them all. HI has the highest boiling point compared to these 3, but HF is the one that has the highest boiling point. But now why? Why is that the case? You need to know your stuff, guys, if we have to be honest. Okay, you know what? I'm gonna erase everything. So when we have a look at HF and HCl, what's different about the two? I understand it's molecular mass, right? The molecular mass of HCl and HF, it's different. But I mean, like, they really cannot just specifically ask us. And again, okay, it's fine. We can talk about the molecular mass. That's why the boiling points are different. But the thing is, when you have a look at F has the lowest, it has the lowest molecular mass, and then Cl has the highest molecular mass. So that means because HCl has the highest molecular mass, HCl is supposed to have the high boiling point compared to this, but this is not the case. HI is the one that has the highest boiling point. Look, I'm saying to you, the molecular mass for H is very high. It's very low. So the molecular mass from the periodic table, you know how to determine the molecular mass or molecular formula. Molecular mass of HF is low compared to this one, but this one has high molecular mass. And we know that the one that has the high molecular mass, it's supposed to has the high boiling point as well. But this is not the case. This is not the case. HCl has the lower boiling point instead of having high boiling point. You see? So that means you're going to be wrong by explaining it referring to the molecular mass. Hence why they say to you, refer to the strength of intermolecular force, not the molecular mass. Then the question is, how are we going to solve this? Now, let's talk about the intermolecular force then. Now, the intermolecular force, HF and HCl. Let's talk about the intermolecular force. What type of intermolecular force does these two actually experiences? Remember, we have what you call the hydrogen bond. Hydrogen bond, the van der Waals forces, right? The intermolecular force though, not the bond between the molecules, the bond, not the bond between the atoms, the bond between the molecules. So we have what you call the hydrogen bond. The hydrogen bond is the strongest intermolecular force out of all the intermolecular forces. So why do we say the hydrogen bond? How do we see the hydrogen bond? It's when hydrogen, it is bonded to these three atoms north. When hydrogen bonds with nitrogen, we are having hydrogen bond. When hydrogen bonds with oxygen, we're having the hydrogen bond. When hydrogen bonds with fluorine, we have the hydrogen bond. And the hydrogen bond are the strongest intermolecular forces out of the intermolecular forces. So we can see that here we have the hydrogen and Cl. Here we have the hydrogen and fluorine. Fluorine is the one that will experience the hydrogen bond. So that means the intermolecular force of fluorine, it has the strongest intermolecular force compared to HCl. Because you can see that HCl will have what type of intermolecular force? Dipole-dipole force. Okay, so that means by referring to the strength of intermolecular force, explain why the boiling point of HF is higher than the boiling point of HCl. It's because HF will experience the hydrogen bond, right? And then HCl will experience the what? The London force. Not the London. The London is the weak intermolecular force. The dipole force. The dipole force. So then the hydrogen bond is actually stronger than the dipole force. The dipole force, right? So the stronger the intermolecular force, I'll just write IMF, okay? When you write it fully, the stronger the intermolecular force, the higher the boiling point. The boiling point. Therefore, HF will have higher boiling, boiling point than what? than HCl. Okay, so this is how easily you can answer this. I told you it does not matter how you answer this. What matters is, do you have the key words? That's what we want. So now here's the thing. You said HF will have hydrogen bond. That's the first thing. The second thing, HCl will have the dipole-dipole force. That's the second thing. The third thing is hydrogen. Now you compare the two forces, the intermolecular forces. Hydrogen bond is stronger than the dipole-dipole force. That's the third thing. So we know that the strength of the intermolecular force, the stronger the stronger the intermolecular force, the higher the boiling point. We know that we said it again. We said it that hydrogen bond is stronger than the dipole force. Now we are saying the stronger the intermolecular force in this case, which is the hydrogen bond, the stronger the hydrogen bond, the higher the boiling point. Therefore, the one that has the stronger intermolecular force, which is the hydrogen bond, which is HF in this case, will have a higher boiling point than HCl. That means, therefore, HF will have higher boiling point than HCl. And then we are done by answering this question.